Good evening, everyone, and welcome to NSimplex Pachinko. This is Obi-Wan Pez, and we're doing some math tonight, so I am trying to investigate why it is that my audio keeps cutting out. And I just created an account at Corsair's website, and then it sent me a verification email, as usual. I went on to the site and typed in the verification number, and then it threw an error. So, yay! Guess I have to wait until tomorrow for them to sort that out. In the meantime, hopefully this will not cut out too much. If I ever just stop talking suddenly, it's probably because this thing has been beeping in my face. I'm about 5 seconds from rioting. And yes, it is fully charged. Or, to, what is it, 90%? Yeah, 90%. Yay, technology. Someone else on their forum basically posted the exact same thing of like it keeps cutting out and beeping at me and all this stuff. And then somebody answered them back and asked like, what did you plug the receiver into? And I'm just thinking like, it's in my motherboard. Like, you can't get any closer. I mean, I could understand if it's plugged into like the monitor or something, that might cause an issue. Come to think of it, do I have one? No, I don't. And OBS just changed all of its overlay type, or the layout that it has, which, I'm not going to complain too much. It's probably fine, but it made everything larger, and I don't need the help. Like, my eyes are good. So I'd be perfectly fine having to look at, tiny little print, basically long distance. I'm good with that. But whatever, it's fine. I'm just gonna bitch all night, it's fine. Went to the kids' back to school night, or the younger ones back to school night tonight, so met up with his teacher, who was also originally her teacher a few years ago. She's like, I'm so glad I get to meet your son. I'm like, hope he's been behaving. And Planet is cool. Thanks for stopping in. 2 times 3, huh? I also briefly talked with the teacher, and I was like, so if you've got any parents who are like freaked out about the Common Core thing, and this goes for like anybody, I'm trying to do some research into like trying to teach Common Core to parents. Just starting the preliminaries here. And she's like, oh, you're starting your PhD? I'm like, no. She just laughed. And then I'm walking outside, and I'm like, the education of parents of K-12 students in mathematics... No, stop it! Damn it. I've only been out of the house for an hour, and already I've got a thesis. Really, sincerely hope that does not become a thing. But anyway, hope y'all are doing fine tonight. And tonight, let's see. What have we got coming up? So we got limits and notation we can do. Can do Common Core type stuff. Oh, that's right in the way. Nice. Perfect timing, man. Also got function properties. Over the next couple of days, I'm going to be teaching transformations, extrema, I very unfortunately put a little sugar in my coffee tonight. I'm not very impressed. The coffee itself stands on its own when it's black. I should have known better. Goodness. Alright. So, I mean, these are just some ideas. If anybody's interested, feel free and comment. Otherwise, I'm going to be just start faffing around a little bit. Alright. So the idea of limits, we've got Blyland. How's it going? Yeah, Pac Northwest is not doing so hot with, or is extremely hot. Yep. That is true, but oftentimes I forget which way is which. So, degrees Celsius, 2 degrees Fahrenheit. We're going to say, since this is 0 maps to 32, this is my way in. So this is telling me that I need to take 9/5 times C, nope, plus 32 is going to get me F. So this is all a matter of noticing where the vertical intercept is in this particular case. I know that I need a set of all right, now that we've got that, like I said, that's my way in. So now 44 plus 32 is going to be Fahrenheit. This is going to be 44 is pretty close to 9. So this is going to be 9 times approximately 9 plus 32 is Fahrenheit. Again, this is just like a quick off the top of the head estimation. This is going to be 81 plus 32. So this is getting into the holy shit range. That's going to be 113 degrees Fahrenheit. So, yeah, I do not look forward to that sort of thing. This is going to be 44 degrees Celsius convert to 113 degrees Fahrenheit, approximately. Yes. This is getting to the point where asphalt will actually start liquefying. Oftentimes, if you are walking on asphalt, either the bottoms of your shoes will start to melt and then refreeze to the asphalt, or the asphalt itself will start actually desolidifying, will start melting. So yeah, this is getting into not good territory. Definitely somewhere where you should be somewhere with air conditioning, and yeah, not staying in the sun for any length of time whatsoever, or parking in the sun for any length of time whatsoever. Ah, did it? Jeez. Work with me on that one. So, what about dimensions? Yep, that is not surprising, unfortunately. Cars can get well above 140 degrees, which is enough to cook meat. So it's extremely bad. Yes, yes. The plastic in your car can melt, and that will also cause potentially chemicals to start permeating the air inside your car. So you definitely gotta crack the windows if it's ever gonna be outside for any length of time. I mean, you can, but you're gonna want the windows open, at least a little bit. and you probably don't want anything in there, which is going to potentially be a problem. Like I said, that's enough to cook meat, which does also mean 140 degrees is enough to cook you. So do be careful. And if your body temperature gets above 105, you're definitely in the emergency range. So be careful with that too. Yep. I mean, just everywhere is all messed up at this point, which is just what we're going to expect with more climate change coming. We keep adding energy to the atmosphere, it's going to become more and more unpredictable. So we're going to get extreme highs and extreme lows. Yeah. I mean, even at nighttime, right? Like, yeah. So, whenever you need the AC, it is there, but then the problem becomes at some point we're going to stress the entire power grid so much that it's just going to fail. So it will either have rolling brownouts or blackouts. And if there's blackouts in this kind of heat, it's an unfortunate thing. Yeah, it's an unfortunate thing, but if we have blackouts in this kind of weather, people are not equipped for it. You know, people end up dying in their homes. It's going to be really bad. Mm-hmm. Yep. I definitely believe it. I mean, so do we. We're trying to use less, which is helping. But at the same time, we're not reducing it fast enough, and we're not able to keep it like going overnight, or keep the renewable energy going overnight to power everything. So at this point, we're kind of overtaxing the system as a whole. Coal has deep output, unfortunately. What we really need is like strong nuclear at this point for everybody to understand that nuclear power is safe comparatively, and the short-term risks are very small, and the long-term risks are also very small. All we really need to make sure that we're doing is storing the spent fuel, and then we are able to, at this point, also create spent fuel reactors. Spent fuel reactors will take the spent fuel that's coming off of primary nuclear reactors and be able to take their waste products and then decommission them even further. So based on what happened at Chernobyl and what happened at Fukushima and what almost happened at 3 Mile Island in Pennsylvania, which is one that you missed, so the thing is that we've been learning about nuclear power ever since then. We've been learning more and more and more as time goes on. So it's not really all that dangerous, especially when you think of like the number of hours that these reactors have been going and how many reactors there are. I believe that was the automated system that recognized that it was going into a meltdown state and like closed off everything in a proper way. The problem with Chernobyl in Ukraine was that the automatic shutoff system like didn't work properly, or somebody, I don't remember exactly what happened, but like somebody slammed the control rods into their off position, and like it caused all of the water in the entire system to just boil like instantaneously. I don't remember 100%. So watch, actually, you know what? It's right. There's a bunch of documentaries. You could even watch Kyle Hill's thing on YouTube. He does a wonderful job explaining all that. He actually got to go to the exclusion zone in Ukraine at Chernobyl and check out like all the cool stuff that's there. Um, that was well before the Russia thing. I mean, sure, it's more complicated in some sense, but like it's not terrible. You just have the proper shielding, you're fine. I mean, I don't know any quantum mechanics, but that doesn't mean it's the hardest. Um, right now, I am struggling with tensor calculus because I'm a glutton for punishment. At least I think I need tensor calculus in order to really make use of my and simplex stuff. So my problem is that I really don't even know what's out there beyond what I've already studied and like the couple of things I've looked at. So topology, generally speaking, it doesn't seem terribly difficult as a concept, but then when you start having to formalize the mathematics and put them into proofs and all this other stuff, I have absolutely no idea what any of that is like. I've never done it before. My spouse took topology and she loved it. It was just absolutely wonderful. And according to her, she had a great teacher. I mean, it really helped. I am not a good, not a terribly good student, quite frankly. So I have been working on TensorCalc, but I haven't been really working that diligently on it. I've been kind of, dabbling here and there and trying to get it done, but at the same time, I've got a lot of other stuff going on. So I'm trying to do my work, make sure I've got all my student stuff corrected, make sure all this other stuff, and then I've got like 5 books I'm trying to read. So so far, the way it's gone is I've taken Dr. Grinfeld's TensorCalc book, and it is in my bag at the moment, and it's been there for a week, 2, haven't even touched it. It's too bad, because, I mean, if I really kept at it, I think that I could finally understand some of it, and maybe even be able to put some of this on stream, and try to get my thoughts. But, is calculus the easiest? I mean, not really. Is it the easiest class that most STEM majors will take in college? Yeah, probably. And it also depends on like which. It also depends on like what school you're going to, because like my school labels calculus in the 100 level, and Calc 2 is also in the 100 level. It's just, the next number up. But really, yeah, I mean, it depends. So, you know, calculus can be easy, but I think that's really if you have the foundation for it, if you understand like the notation and everything you were supposed to know from pre-calc. If you've got all that, if you've got the algebra background, then again, calculus concepts are super easy. Just like, you know, um, what did I just say? Topology. Just like topology. Topology concepts can be super easy. But then, like, formalizing everything and needing to know how to put the algebra on the paper can be really hard for a lot of people. Now, I found calculus pretty easy because I was very regimented in the way I was doing algebra. And when I did pre-calculus, like, I think I told you this, I had proved the change of base formula. So I went through and I said, okay, I know that I've got log base b of a, and I need to prove that this is equal to log base c of a over log base c of b. Computer science math. So my roommate and my friend was somebody who was a computer science major, and he took formalization, I think was the class, which had, it seemed to me to be sort of like, here's a concept that you need to figure out, here's an algorithm that you need to follow, and how are we going to get this data into a mathematical formula or something like that. I'm not even sure exactly what happened. He noted that the previous class had a pass rate of 39%, and his class rate had a pass rate of around 31%. Like, I don't think it must have been a very good class, because that teacher just like, yeah, I don't know. It's like the department thought it was a necessary class, and also they were just willing to like let that many people fail. Like, I don't even know. So I don't think that it must have been taught very well, if that was what was going to be. What did I do? Well, these days anyway, I would take this and I would say, okay, log base b of a is going to be equal to some dummy variable, which I'm going to call x. And then this is going to end up being b raised to the x is equal to a, because again, log base b of a means what exponent on a base of b is going to get us a. So what exponent on a base of b gets us a? B to the x equals a. And then you think you are in error for going for computer science? So then here I'm going to take the log base c of b to the x is equal to log base c of a. Here the exponent x comes down front. We get x is equal to log base c of b. That's not what I wanted. Not equals, multiplied by. Alright, x times log base c of b is equal to log base c of a. And then x is equal to log base c of a divided by log base c of b, which is equal to, as we said up front, log base b of a. So, I've mentioned this before, but this is what I did a long time ago, um, when I was in pre-calc, and managed to prove the change of base formula, which my teacher was, you know, mildly impressed because, hey, a student actually took the time out to, like, prove this, and it wasn't a requirement, it was just kind of like, haha, I figured something out. And she was like, oh, that's pretty cool. Why don't you present it to the class? And I was like, okay. So I went through and, you know, showed the class how I did it and all this stuff. And then, come the unit exam, I look on the paper, I flip through, do a couple of problems, whatever, and on it is prove the change of base formula. And I just look up from my paper, and she just goes, and then goes back to writing something, and I was like, oh, you knew. So I think she added that question to her exam on purpose because she knew I was going to get it, right? And I presented it to the entire class. So at least some of them would have gotten it as well. And I don't know. It was just one of those fun little moments. It might have been slightly mean to other people. Yeah, sometimes I don't feel very smart. And really, I do need to... I'm certainly not dumb, I guess. But, you know, the important part is being willing to learn and take some risks and figure out, you know, figure out if there's another way. No. If you got an A in Calc 2, clearly you must have come away with something. Because I very much doubt that that was a pity A. Alright, so you got your limits. So these are values that we're going to approach as the input value approaches a given value. So we had talked at some point when we had done, you know, other calc stuff. You get values like this. If we're going to go with, like, I don't know, 5. And then let's say this is 5, 2, and this is 5, 7. Right, so here, got some function, which is a piecewise function, has these pieces to it. Professor V. Okay, math with Professor V. Ah. Okay, I don't know that I've actually seen her stuff. Interesting. Okay. Well, I will check that out for later. Come on now. Alright, this is gonna turn on at some point, and I'm trying to stop it. There we go. Cool. Yeah. You know, if you don't provide actual, like, lectures for the material, It's very important that your teacher points you to resources. So they've got to have a list that's already pre-done. And if they don't do that, that's a problem. If you don't like their resources, that's also a problem, but it's a different problem. Okay, so for this thing, we've got a function, f of x, and then we got 5 here. Oh, I know, right? The problem is that I can't give you a credential. They can. I mean, I guess I could give you a credential at my institution if you took my class, but that would be many problems. No doxing. So, f of 5 here has a particular value. And in this particular case, again, we want to know what is the function value actually at 5. So the function value at 5 is where the black dot is. That's going to be our 2. And then we talk about the limit. So the limit as x approaches 5 of f of x must be the same as the limit as x approaches 5 from the negative side, or the left, of f of x is equal to the limit as x approaches 5 from the right, or the positive side, of f of x. This semester I've got 1 Calc 1, 1 Pre-Calc, and 2, you can't see those, and 2 Pre-Calculus first half. So function analysis is going to be the first half of the pre-calculus sequence. Oh yeah, no problem. So we've got to say, when you've got limits, it has to be true that in order for the limit as x approaches 5 of f of x to exist, it must be the same as the limit approaching from the negative side and the limit approaching from the positive side. So in this particular case, this particular limit as a whole does not exist. All right, because the limit as x approaches 5 from the negative side is not going to be the same as the limit as x approaches 5 from the positive side. What do we mean by limit? Again, this is the function value that we are approaching, given that the input is approaching the given value. So if as our input starts approaching 5 from both the left and from the right, we got to see what exactly are we going to approach. Yep. So the limit as x approaches 5 from the negative side of f of x is going to be equal to the function value that we're getting closer and closer and closer to, which is 7, that open circle. And then the limit as x approaches 5 from the positive side of f of x is equal to what we're approaching from the positive side is this value here, which is 2. So, because these things are not equal, again, that limit up above does not exist, cannot possibly exist. So its constituent parts aren't the same, so it can't exist at all. Okay, then we could have other situations which occur, and one of my colleagues was showing the students from my class this Friday. Of course, they're also pre-calc students, so they don't technically need limits or have limits in their curriculum, but I'm teaching them the basics of how limits work anyway, and some of them are just like, I don't get it. I'm like, well, you're not really technically supposed to get it. It's fine. Don't worry about it. You hope you don't see limits again. Oh, my friend. Are you in for a disappointment? Okay, so we got something like this, which could occur. Where up here, we've got, I don't know, 2. Let's do 4. Let's do 2, 0, and 2, -2. Alright, so these are these 3 points that are given here. Yep, jump discontinuity. In this particular case, we've got a discontinuity here, which is different from the other 2 values. So it doesn't really matter what they are. I'm just going to say it's 2, 4, 2, 0, and 2, -2, just for fun. Doesn't matter. But for this particular case, we want to say, all right, what's the limit? Oh my God, stop. Of, we'll call this one G because it's totally different, of X as X approaches 2 of G of X. From the left, again, in this case, we're saying what value are we approaching? Well, we're approaching the Y value given here, which is 4. The limit as X approaches 2 from the positive side of G of X is going to be equal to, this goes down further this way, -2. Well, yeah, but L'Hopital's rule you're not supposed to do until the end of Calc 1, so. And again, since these are not equal, the limit as X approaches 2 of G of X does not exist. Yeah, that's true. I guess also yours is broken up differently, so it's possible that we were doing improper integrals. Yeah, right, because you can take the limit of this stuff. Okay, and in this case, our nope, not function f, our function g of 2 is going to be equal to 0, which is completely different than the other numbers. So again, our function value is where is it actually, whereas the limits are how do we approach from one side or the other. All right, and then so for both of these cases here, let's call this h of x and this one j of x, because that's fine. So for this, the limit as x approaches whatever this might be, x equals 3, x equals 3, because I'm just not going to bother with coming up with numbers at this point. As x approaches 3 of h of x, and the limit as x approaches 3 of j of x are going to have values. So in this case, we have, you know, y equals 7 and -5. I don't know. I'm just making stuff up at this point. So if our y value is -5 here, we got 3, -5 as our point. The limit value of that particular function, h, is going to just be -5. And the limit value of j of x for this particular function is going to be 7. Because again, it's not what the function is, it's what the function is approaching as we get closer to that value, closer to that x value. One of my students also asked me if I could set up something because they need to be at like their kids, you know, parent-teacher type conference during the day. They were like, so can we set up some sort of thing so I can still like dial into class? And I'm like, I don't know that I can do that. Might constitute some sort of issue. Alright, Corsair, come on now. Come on now. Oh my god. I mean, you can. Not sure it's a good idea. So we've also talked a little bit about the series and sequences on the stream. So if you had like n goes from 1 to infinity of, yeah, what do I want to do? 1 over n squared plus 3, something like that. And what you'd want to do is show that this particular series is going to either diverge or converge, comparing it to something else. So if we compare this to, and goes from 1 to infinity, just 1 over n squared. N goes from 1 to infinity of 1 over n squared will converge by p series. So this is a particular property that's given, that an infinite sum of 1 over n to the p will converge given that p is greater than 1. Yeah. But it works. Cursors. So if we already know that we have something that will converge, then we try to compare this to what we've got over there. So this one here. What we've got is a series too straight, but whatever, it's fine. A series that looks like this, and what we're going to need to do is find all right, no, the comparison series must be smaller, no, larger Alright, so the comparison series must be larger than the to be tested. For all values of n except a finite number of values. Because again, if we have an infinite series which will converge, then a finite number of values is still going to converge. That's really all we're testing here, is will it converge? That's it. So here, if we want to compare this to the original, we can say, all right, look, for all values of n greater than or equal to 1, we know that n squared plus 3 will be greater than, strictly greater than, n squared. So 1 over n squared plus 3 will end up being less than 1 over n squared. So therefore, by what we just set up here, the comparison series must be larger than the original. Well, that's what we've got. The comparison series is going to be larger than the to be tested, the original series that we had, by this constant addend of 3 in the denominator. So that's always going to be larger. Sorry, the comparison series 1 over n squared is always going to be larger. So that allows us to say, well, since this is always smaller, it must be a smaller amount in total. I mean a little, but you know, graphically, maybe it'll look a little bit better. And I'm doing it all wrong because I don't have these particular values, but so whenever you do 1 over a number, it changes how large it is. Right? Big numbers become small, small numbers become big. And so if a number was smaller, and then you do 1 over both of those numbers, that now is going to become larger, because it's taking the multiplicative inverse of this thing. So, you know, we can go with an example, like 10 versus 1,000, right? 1 over 10 versus 1 over 1,000, right? So in this particular case, 10 is going to be less than 1,000. And no. And then down here, 1/10 compared to 1/1000th, 1/10 is bigger. Yeah. So they have an relationship to inverse relationship to each other, just like the functions themselves. You didn't learn like rational functions? Well, we can right now. Provided that this thing doesn't keep crapping out on me. Jesus. All right. Well, there's our two parent functions. So the most basic rational functions are these two things here. F of x is equal to 1 over x is going to be the same as y equals 1 over x. And this is going to be the same as x times y is equal to 1. So what this is saying is that the product of your x and y values are going to be a constant. Now, what constant it is dependent upon what function exactly it is that you're looking at. So in the basic parent function case, you've got 1 over x, right? So x times y equals 1, or y equals 1 over x. Most basic you can get. They are reciprocals of each other. So, if we want to graph this, then we're going to look at this and say, okay, here's your x values, here's your y values. Now the easiest one to do is going to be 1, right? Because here we got x times y equals 1. Okay, what are they going to be? You can make it as easy as possible. Make it 1, 1. Okay. So, 1 times 1 is 1. Cool. What else? All right, well, let's do negative side. Negative 1 comma negative 1. Right? Negative 1 times itself is also going to be 1. Okay, cool. Now where do you go from here? Well, I prefer to think of this in terms of what else are we doing. Let's not put that there. Let's put that on the other side. So how can we get to other numbers? Well, if you look at it in terms of like, where's the... like, what happens if you alter either your x or your y value? Okay, well, adding and subtracting is going to cause an undue mess. So let's not worry about addition and subtraction at the moment. What if you multiply your x value by 2? So if you double x, what happens to y? We've got to keep a constant 1. Right? This has to stay the same. It's a steady state. So in order to get 1, if we end up doubling our x value, what do we have to do to y to keep it the same? Well, the x and the y have to be the same. So here you could say like, okay, I'm going to multiply by b. So therefore, 2 times b times x times y is equal to 1. Those have to stay the same again. This needs to return so b must be equal to 1/2. So if we double our x value, we are going to have to balance by halving our y value. So we double our x value. Now I'm going to say value, but really this is the distance to the origin point. All right, so we're going to alter this in the future. So it's going to become important. So if we alter our origin where we are, then it's going to change things. But the thing that I'm talking about right now, the distance in the x direction, is always going to have the same pattern. So find a home value or an initial value that is on this function that you can choose. Doesn't matter what it is. If I pick a different one, the same pattern will exist. So like I said, doesn't matter. So I'm going to take this value, a distance of 1 in the horizontal and a distance of 1 in the vertical. I'm going to double my horizontal to 2, which will, at the cost of the other, we have to balance by halving the y distance. So double your x, halve your y. Double your x, so from now 2, we're going to have to double this to 4, halve your y. It's now 1/4. And look where we are. We are at 4, 1/4. Well, no kidding, right? That was because here we said our y values are the reciprocals of the x values. So our x value is 4, our y value is going to be 1/4. It's the reciprocal. All right, now let's go the other way. Let's halve our x value, which will consequently double our y value. Okay, this gets us now to 1/2, 2. Again, they're reciprocals. No kidding. Halve our x value again to 1/4. It's going to double our y value to 4. Okay, and then now we've got this curve here. And you can add more points if you want. Make it, 1/3, 3, or 3, 1/3, because again, those are reciprocal pairs. It's going to work. You could do it on the negative side. So again, we've got an initial point at -1, -1. Halve our x distance and double our y distance here. Halve our x distance, double our y distance down to 4. That's going to be off the chart, but it's close enough. Double our x distance, get us out to -2, halve our y distance, get us down to -1/2. You can barely see it, but it's there. Do the same, double our x distance to 4, halve our y distance to -1/4. You're gonna have to trust me on that one for a minute. Yeah, there we go. Alright, -4. There. Alright, and then do your best here. It's gonna be a little awkward, but yeah, it'll work. Alright, and then what's going to happen? Well, I'm going to keep doing this, so I'm going to keep doubling my x distance and halving my y distance. We're going to get closer and closer to this value of 0, but the thing is, we're never actually going to reach it because we keep halving the distance instead of like adding a certain amount. We'll never get to or past 0, at least not from this direction. Right? Same thing on this side. We'll never get to or past 0 in this direction. It's just going to keep going and going and going forever. So this is asymptotic to our x-axis in both directions. It's also, consequently, asymptotic to the y-axis for much the same reason. Again, we keep halving that x distance, but our y distance keeps doubling, or as our y distance keeps doubling, our x distance keeps halving. And when you just half and half and half and half and half of stuff, there's going to be something that's left over. There's always a distance to cut in half. Well, you discard half of it, and then you keep half of it. So there's always something there. As infinitesimally small as it eventually gets, there's always something. So then this is going to be going like this. Oops. Okay, so this is the scheme for our rational functions, our distances, not our function values. It's the function values for the parent function. This one right here. That one. That one right there. Right? That parent function has this scheme for its function values. But all rational functions that have a 1 over x as its core thing. We'll talk about transformations in a bit, but 1 over x as its core piece. This is always going to have this scheme as its distances. No matter where you transform to, it's always going to have the same scheme. Have your x distance, double your y distance. Always, every time. Don't believe me? We'll do an example. But over here, g of x, all right, we got to do this one first, is equal to 1 over x squared. So what do we do with this one? Well, this... 2, 4, 3, 2, 1, 0. 1, 2, 3, and 4. Okay, x values, y values. 1, 2, 3, 4. All right, so what are we going to, either way, it's going to mess that up. So what's going to happen here? Well, same deal. This time, though, this is y equals 1 over x squared, or x squared times y is equal to 1. So we're going to square the x value, and then the y value has to be the reciprocal of that. All right, we could see it either way here. Doesn't matter which one you really focus on. It's the same stuff. So then we end up with, right, 1, 1 is still the easiest thing to plug in. what happens when x is -1? If x is -1, we end up squaring it, and we get 1. Times what is equal to 1? Well, y equals 1. So this is also going to be a positive value. That is Utica, I believe. Thank you for the follow. If you're lurking, don't worry. Don't need to speak up or anything. Hope you are having a nice night, and hope you're enjoying the math. Alright, so it was kind of foolish of me even to bother with all this stuff down here, because we don't need anything in the negative region. Don't need any of it. Alright, now, this becomes slightly awkward, because it's not going to be just the same as the other one. What we've got to do now is we've got to say, okay, if we double the x value, what happens to the y value? So we double our x value. Again, let's do b times y equals 1. So we've got to do something to the y value, but we don't know what yet. Here, this is going to make a 4x squared times by is equal to 1. And again, 4 times b times x squared times y is equal to 1. And must return so b must be 1/4. So if we double our x distance, we're going to have to cut our y value by the square of a half. So cut it into a quarter what it was before. So here we have a value of 1. If we double our x distance to our x distance to 2, now our y distance is going to be cut by a 1/4. So now down to a half and down to a 1/4 right here. All right, same on the other side. Our distance here gets doubled to 2, and our y distance gets cut to 1/4 what it was. Then we take this distance, which is 2, and we double it to 4. And then we're going to, again, divide by 4. Because again, we doubled, so our x value is multiplied by 2. Now our y value gets cut by 4, a factor of 4. So a half of that and a half of that is really small. And again, this doesn't actually come up until about here. So this crosses the line entirely. Okay, and now we've got to do the same thing as we did before. If we cut our x distance by half, this is going to do the same thing up here. A half squared is going to be 1/4. So then in order to make it up, our b value attached to the y has to be 4. So now we have to quadruple our y distance up to 4 if we have our x distance. So again, have the x distance, quadruple our y distance. Okay, and on the other side too. All right, so in this case, again, we have the same asymptotes. We're going to have x equals 0, where we're never going to get any x value to hit 0, and also y equals 0. Our y values are not going to hit 0. They're going to keep getting cut in 1/4 every time you move, or every time you double your x distances. But cutting by a factor of 4 over and over and over again still leaves something behind. So it's always going to be a little tiny minuscule piece that's left over every time. All right, so what if you see something like y equals 2 over x minus 3? All right, what is this going to do? What are you going to do with it? How do we analyze this particular function? Well, we want to know, when is it that you end up with a product of two numbers that is equal to 2? Right? So this is going to give you a hint in terms of what you want to do with like finding an initial value. It doesn't really matter how you do it. However, I would say, look at this right here. If x is a certain value, then we're going to have a problem, because you'll find that there is no y value for which you will get 2. All right, so this is fairly easy to recognize, right? If x equals 3, then y will have no value for a product of 2. So therefore, x cannot be 3, ever. Just like up above. Now, I didn't actually mention it here, but I probably should have. If we look at that in terms of this multiplication here, x times y equals 1. There are values for both x and y where we can't have them. Right? So x nor y can be equal to 0, because here that would mean that 0 times whatever you want, it doesn't even matter what this is equal to 1, or x times 0 is equal to 1. But again, you can't do that, right? Either of these would mean that 0 is equal to 1, and we know that that's not true. Right? 0 and 1 are distinct numbers. They have a number that's between them. Therefore, they are distinct. So for this one, we know that x cannot be 3. We also know that y cannot be 0, just the same as it was up above. That's not what I wanted. Y cannot be 0. So this right here tells us exactly what our asymptotes are going to be. This is going to get ridiculous. So 3, 4, cool. All right, so this is going to be our x, this is going to be our y. Okay, x equals 3 is going to be our asymptote. Y equals 0 is going to be our asymptote. Yeah, that looks really nasty. Must have been making up for being too high on the other side. Okay, so y equals 0 and x equals 3. Going to be our asymptotes. We can't have these values ever. All right, our original function. There are kind of two ways to go about this. One is you could plug in values to get 2. So find a factor pair for 2. 1 and 2. All right, when does x minus 3 equal 1? Well, x minus 3 is equal to 1 at x value of 4. So an x value here of 4 is going to get us a y value, nope, a y value of 2. Because again, we said 1 times 2 is equal to 2. So 2, 4, negative 2 there. All right. Now here's the thing. This is the initial point. Cool. Now what? Well, double our x distance, halve the y distance. Double the x distance, halve the y distance. Halve the x distance, double the y distance. Our distance is going to be measured again from the origin point, which is the place where these two things meet, right? The place where our asymptotes meet. At least for this function, right? There's always some possibility that it's a different function. All right, so halve our x distance, double our y distance. Now we're up here. And this is going to be 3.5 comma 4. Okay, this is going to be 4 comma 2. This is going to be 5 comma 1. This is going to be 7 comma 1/2. Okay, on the other side as well, we've got the same thing going on. Our initial value is going to be 1 over and 2 down. This is going to be 2 negative 2. And then again, halve the x distance, double your y distance. It's going to be 2.5 by negative 4. And then over here, double the x distance, halve the y distance. Double the x distance, halve the y distance. So it's going to be negative 1 by negative 1/2. 1 negative 1. All right, and then we get all these points, which again, oops. Okay, so there's a few different ways to look at this. One is, kind of my favorite here, is that you've got this term here, x minus 3. This is taking this whole function and it's shifting it right 3. So how do I know it's shifting it right 3? Well, it's doing the same with y equals x versus y equals x minus 3. This is shifting it right 3 places. All right, and also, if you're not sure about that, you can also notice that here we would get another point, not just 3 comma 0, but also 0 comma 3, negative 3, 0 comma negative 3. So this is saying that from 0, 0, our origin point, by putting minus 3 on the end of it after x, we could have either caused this to move down 3, or caused it to move right 3. Whichever one's most convenient. Now, on a bigger function, where our internal and outternal parts here, I can't even finish that. Where the internal and external pieces of the function are. So if you remember, I did this a long time ago. The possibilities for a linear transformation are y equals a times function of b times, parentheses, x minus c, plus d. So all of these pieces do something, and your job would be to figure out what they all do. Now, honestly, the easiest way to do this is in Desmos, because all you need to do, let's see, where is my browser window, and is it compromised? It probably is compromised, so let's change this to something innocuous on all of them. I mean, that's innocuous enough, but let's just add it anyway. Right, again, innocuous enough, but let's bump that over as well. Sure, why not? All right, that one. All right. Okay. Okay, so the way to work this out, easiest thing to do, y equals a times f of b times, parentheses, x minus c, and, oops, lucky. There we go. All right, parentheses, parentheses, cool, plus d. Okay, that's interesting. A, okay, there we go, B, C, and D in the complete wrong order. So, all right, just drag. All right, now it doesn't know what I'm doing, so we have to choose, nope, f of x equals 1 over, oh, that's not good. F of x is equal to 1 over x. All right. So when we do this by default, A and B are going to be 1. C is going to be 0 because we're not adding anything or subtracting anything. D is also going to be 0 because we're not adding or subtracting anything. Then we want to be able to say, okay, the red one is going to be the transformed one. What's going to happen as we do all of these things with A, B, C, and D? So as A, we'll come back to that. Actually, you know what? Let's do plus C here. Right, as C increases, we notice that here, the function itself is actually decreasing in the x direction. So it's going that way. And as we decrease, it's going to increase in the positive direction. So here, it's actually more convenient to use a negative c, or x minus c, so that when we go to the right, when we increase our c value, we're increasing the value of the move to the right-hand side. So c is positive, but what's visible here is x minus c. So now that bit is going to appear more negative. All right. So our C value, as we increase C and make sure it says x minus C in the function transformation, then we're going to get, again, something that moves in the same direction as we're kind of used to. So as we increase the value for C, it moves to the right. As we decrease the value to C into the negative direction, it moves it to the left. And of course, that's opposite what we would visually see if it were just written out. So, x minus 1 is going to be, well, C is 1. Okay. So let's move that just over so we can understand why that's there. And D, adding to the outside of a function, is going to then increase the function value. So it's going to increase the value, it's going to move it up. And then likewise, decreasing the value because we're subtracting from the original function value. Okay, and then the slightly harder ones, you've got your b value here, which is on the inside of a function. It's going to treat your x value that's being plugged into the function as if it were some number of times bigger than it actually is. So if you have it be twice as large, your 2 is on the inside of your function, then what's going to happen is all of your function values are going to be taken from an x value that is twice as large as the one you're on. So, for example, a value of b equals 2 for b equals 2, let's move that back. Right, compare b equals 1 with b equals 2. That's bigger. So can keep increasing, that's fine. Up to 10 in this one. So here, this is causing us to have values for our function. It kind of looks like it's moving to the middle, but that's actually not what it's doing. If you're just changing b, then what you're doing is you're changing the horizontal distance that we're traveling here. So b equals 2, we should be able to see a few values on here, which are going to be important, right? 1, 5. 0.5, comma 1. Right, 2, comma 1/4. 1/4, comma 2. Oops. Boo. Anyway, you can see it's pretty close to 2. Okay, so all of our x values are being pushed in by a factor of 2. And then here with our a value, it's multiplied on the outside, so you take your function value as it's coming out of the function and you multiply it by whatever that value is. Right now it's 1. As we multiply by 2 and 3 and 4, that's going to, it's going to cause it to look like it's moving out again. But b, it's also multiplying your y values directly. So if you look at this, you could say if we had an a value of 4 and a b value of 2, then this is going through the point here, -2, -1. Reason being that it's taking its b value of 2 and saying we're going to treat this as if it's a number that's twice as large, so it's going to take its q from -4. -4 in the original function ends up getting us -1/4, and then we've got this a value here, which is going to multiply by 4, so we're going to get a -1, but that's on an x value of -2. All right, then if we shift this over, again, all this is doing is putting the asymptote here at x equals 3. You could still count just the same, so left 1 and down 2. Is the same stuff that we have over here. So here, left 1, yeah. So here, left 1, down 1 gets us to the original point, and then again we're multiplying our function values and the internal part by 4 and 2 respectively, and that's going to change again. It's going to change its horizontal compression value and its vertical stretch value. All right, so in this particular case, you can't see that. Hang on. In this particular case here, we said that the initial value that we wanted to pick was going to be 4, 2 by looking at what we had here and just saying, okay, well, it's 1 over from the asymptote. Let's go with that. Yeah, that could work. You could pick any value you want as your initial value. You could have picked 5, right? 5 minus 3 as your initial value would be 2. And then 2 times 1 is 2. So now 1 is our y value. It's set. Our x value would then be 5 minus 3 is 2. So 2, 1. Distance of 2 earned from a location of 5. So x equals 5. Because we're taking from x equals 3, we're adding 2. 1, 2. And since we're going over 2 normally, we would get a y distance of 1/2, but then we're doing a vertical stretch with our 2. So vertical stretch stretches from a distance of 1/2 to a distance of 1. And that's how we get 5, 1. All right, now we could do something crazy. Mix all of them together. No, that's not what I want. Jeez. All right. So if we did this as y equals 3 divided by 2x minus 4 plus 7. No, that's a bad idea. Plus 1. Over here, we've got a common factor of 2. So this could be 3 divided by 2 parentheses x minus 2. add 1. In this particular case, we've got two options of things we can do. One is that we can take our 3 and our 2 as one fraction and let our a value be 3/2. Perfectly valid, works great. If you don't like fractions like most of my students, or if you just want it to be slightly easier, we could say that in this particular case, our vertical stretch factor is 3 and our horizontal compression factor is 2. Both of these things acting together might be a little strange, but it's all right. So we could take this and say, okay, x minus 2 means that we're going to shift our origin point right 2, and a plus 1 at the end means it gets shifted up 1. Okay, and then from here, normally, we have a distance of 1 and 1 to get to the initial point. It's not where it is today. Because again, what we did here, we multiplied its y distance, we halved its x distance, we moved it right 2, and we moved it up 1. So now stuff's in many different directions. So from where it should be, if it was just a 1 over x minus 2 plus 1, the b value is going to halve our x distance, and the a value up top is going to triple our y distance. So a distance of 1 now becomes 1, 2, 3. So this is our new initial value. Now, if you don't like that, that's perfectly fine. You could have said here, well, this was 1 normally, so where would it be normally in order to get this stuff? Again, this would be a value of 1.5. So instead of 1, it's going to be 1.5. Our second point would be there, in the middle of the 2, of course. Where it always belongs, right? And I won't have to move that, I don't think. Now we got to get rid of the points, though. Alright, so from here, again, this is where it is normally. So from there, instead of there, we've got now a value of 1.5 at the same x value. Or leave it at, or cut the x value in half and then triple the y value. 1, 2, 3. Do the same on the opposite side. So instead of this point here, we could say, okay, that's going to be 1.5. There's a little marker there. And then we could also do the same for this one. Cut the x distance in half and then double our y distance. Or use the a value here. So 3. All right, and then keep going. So first of all, we got to get the asymptotes in. All right, so x equals 2. And here, y equals 1. Okay, again, double the x distance. So that's out to here. And we're going to have the y distance, which ends up getting us to become, to get a y value of 3/4. Down here, you could do the same. Have the x distance double the y distance. So instead of 3, this is going to be 6. Again, here, this is 2, so double our x distance to 4, halve our y distance. Down here, you could do the same thing. Halve your x distance, double your y. I'm going to point up there now. And then over here, take this point, double the x distance, halve the y distance. Okay, double our x distance to 4, halve our y distance. All right, with that, this is the, my goodness. All right. So that's what that looks like when we have a function that has all 4 transformations visible right here. Again, you can treat A and B as separate or together, whichever one you choose, but it has to be one of those things. All right. I think I'm going to call it because I'm losing it. Pretty bad. So, let's raid on over to who else is on tonight. Alright, so let's raid on over to Dev the Devastator. He's a friend of the stream and nice guy. I will say that this is technically probably going to be considered a mature stream, so those of you who aren't 18 over, you probably want to leave the raid. Sorry. Normally, when I was streaming on Wednesday nights, we have Jason Charles Miller, who is also an excellent musician and generally speaking doesn't really swear all that much, you know, just doesn't like to. So we usually raid him, and he's nice and clean most of the time. But we're on Tuesdays, so we're not doing it anymore. And I'm on an ad, so I'm not actually, you can't hear me, maybe. Of freaking course. Okay, well, I guess I'll speak to you on video on demand. So, hang on. Okay, let's try that again. So, we're going to raid Dev the Devastator. He does have a technically mature stream, so those of you who aren't 18 may need to leave. And anybody who is interested, thank you very much for coming. My name is Obi-Wan Pez. This is N Simplex Pachinko, my home for mathematical things. And I hope that I will see you next Tuesday for math or Fridays for gaming stuff. This week we're probably doing more Elite Dangerous because we've got all sorts of crazy stuff going on. If not, then we'll probably just be doing some base building in Valheim, or starting something new, I guess. Maybe keep going on Final Fantasy VII. So anyway, have a good night. This is Obi-Wan Pez for Ensignplex Pachinko. See you hopefully next Tuesday. And away we go.